Okay, so let's move straight on. Let's see, just minimize this out of the corner of my view. Okay, so we're going to talk about really today RIQAS reports and how we use them basically to help us detect errors within the lab. Just a few slides just as an intro to this whole topic. We are very much aware that errors occur in all various aspects within our laboratory experience, through the pre-analytical, analytical, post-analytical aspects that we have to all work in. And errors occur, basically can occur at each stage. So that's obviously can have a big impact because what is estimated that about 2/3 of that information from the hospital labs, from the labs that, yeah, sorry, should I say it's not mainly just hospital labs, because obviously we work with veterinary labs as well. But that information is used to make your diagnosis. If you get that testing wrong, then not only can it have an impact on simply on having to repeat your tests, misdiagnosis, but where then that goes unnoticed, where you may have inappropriate treatment, all resulting in increased costs and time, and of course patient care can and may be compromised. So this is why we have a quality system and why we put a quality system in place to detect errors on a quicker and therefore reducing their impact. So obviously that has changed over time. As Depeche was saying, I've been here for 29 years now, and lots have changed over that time. In the early days, we would have had this sort of situation here, where people simply recorded their results on a notebook. Even we had some very good examples in the past where very meticulous notes being taken, but obviously then that is very difficult to see trends. It's really only very useful for eyeballing your results. So the way things have changed is, of course, then we moved on to having more graphical presentations, use of Levy-Jennings charts, where then you could introduce other rules, multi-rules. For example, Westgar rules are well known. But that in itself, still only for looking at internal QC, is limited. So really what we want to do is extend that out. So not only are we looking at your internal QC, but we're also looking at your external quality assessments. And in between that, then we have the use of other systems, the likes of the Randox 24/7 system, which is a peer group system, which sort of meets that sort of point in between. But really, why do you need the two? Well, this graph here hopefully represents that. So on any single measurement that you have, then you measure the same internal QC multiple times, for example, then what you'll finish up is a mean value, and you'll have a normal distribution for 1, 2 standard deviations away from that target. So this, obviously, this precision or this imprecision that you have, this variability, is what you're using for your internal QC. So that's basically you're saying how your performance, basically measuring the same control time and time again, then how repeatable is that measurement. But it doesn't actually give us any indication of how correct that actual target is. So this is where we have then EQA coming in, where we're trying to determine the bias. So how far away is the mean away from what the true value or what a reference value actually is. So what we normally look at then for any sort of measurement, we're looking at a total error. So we're looking not only at your precision, but you're also looking at your bias. So any measurement that you have will have both components. Why do we have this 1.96? Well, this is basically giving us a 95% confidence in your precision. So any measurement, then looking at 2 standard deviation range, that's your 1.96 factor. So you have a 95% confidence. Add that to your bias, and then that's what you have, your total error or your total analytical error. So why is that important? Just 2 charts here, 2 histograms showing a nice normal distribution. If this point here, represented by this blue and red dashed line, if this is an important cutoff point, then what we're saying is whenever you measure a sample, which is coming up close to that, then you will have a certain amount of uncertainty in your measurement. So there will be come to a stage where if our cutoff is 40 and we know what our measurement of uncertainty is, we know we'll get to a stage, well, in this case here, we'll just use this example, that's 38.2, where we know that we're 95% sure that our result will be below the cutoff. Once we go past this point, then where actually the uncertainty is greater than 95, well, I should say, the uncertainty is less than 95%. So we're less sure of how accurate the actual result actually is. It actually goes the same way around. Once you go past the cutoff, it's basically the same idea. So there'll come a stage where if the cutoff here is 40, then you'll need to go past at least a certain point, certain concentration, where you can determine with 95% confidence that your result actually is past the 40. Because with any measurement, there is imprecision. But once again, what this doesn't take into effect is a bias. So this may be correct, but then again, it may be having influence of a bias on it as well, which may completely shift your performance up or down. So really what we're wanting to find is a way of improving our precision, and also then improving the trueness of our results. Very often what we get is a case of trying to improve the trueness of the value, but we're not actually improving the overall precision. Because of that, then it's still random results, and you're still not 100%, well, trying to increase the confidence of determination of what the actual result actually is. So really what we're trying to do is to improve both the precision and the accuracy, or the trueness, sorry. So that will improve our overall accuracy and therefore decrease the uncertainty in the value. So where does EQA come in with all of this? Well, as we say, precision is normally taken care of by your internal QC, and your external quality assessment is where we're trying to determine the bias aspect of that total error. So as we all know, participation in a scheme in itself doesn't lead to improvement in your quality of your analytical performance. We need to interpret the reports, we need to come to a conclusion, implement corrective actions, and also check the effectiveness of those corrective actions. So the way that we've developed the reports over the years, we've tried to make them as graphical as possible to try and provide you with basically the valuable information that you need on your performance, make it easy and quick to interpret, and basically so that you can implement your improvement measures on a faster turnaround. So once again, it reduces the time frame to hopefully reduce then the errors that you're potentially having in your system. So very quickly then, we're moving on to actually looking at the actual reports themselves. Now we're very much aware today, for those people that are here with us, some of this will be very familiar with you. We have some very long-standing participants joining us today. So some of this will be not new to you at all, but yet we're very much aware that we have other guests with us today where this may be new. So please, we are going to cover a lot of maybe old ground, but it certainly may be new for some. Once again, hopefully you may pick up a few aspects, even if it is very familiar with you. So the actual quantitative reports is displayed. It's a 7 sort of sub-reports are displayed on a single page. And we're going to go through each of these really in turn to see all the details that they include. So the first one, basically a text section, is the main one, which contains all the statistical information. I'm not going to explain the actual stats at this stage. Once I go through the report, then Sally will take over and actually go through the statistics. So that'll come just at the next stage. Okay, first thing to note here is you get 3 lines of statistics normally. That's not always the case, because we do have some of our reports where we only present the 2 lines, which would be a null methods and a method. But in that case, the method itself tends to be instrument reagent specific. But for the likes of the clinical chemistry, urine, drugs, proteins, most of our quantitative, then it is 3 lines of statistics. So it's broken down in a way here. So you have N for the number of returns which have been submitted and used for the calculation of the mean. Now, there are also then this 189 in this case excluded. So altogether, this is the total number of returns that were actually submitted to us. 189 results were excluded for the generation of this mean, this target. The CV is based on 1 standard deviation. So that's the CV of the mean. We have the uncertainty of the mean, and we have an SDPA. Now, Sally will be going through explaining those in more detail later on. But really what we're saying is your main comparison group will be at the instrument level. We base it on having at least a very minimum of 5 results. If you don't have 5 results for your instrument, then it'll move up to your method. If we don't have 5 in your methods, then it'll move up to the all methods. But thankfully, because of the size of the database that we have, then very often that's not the case. We have plenty of participants. But you do get new systems coming online. You do have new specific methods coming online. And similarly, you have old methods dropping off. So at some stage, you will have new systems coming on, and so the numbers may be low, or as a new system is sort of leaving, then once again, the numbers may drop. So, but your main comparison group will be against your instrument in the first place. Okay, the next section down is where you have your result that you have submitted. It's going to be indicated on the histogram with a triangle. It also will have the mean for comparison that's used. As you can see, this is color coordinated. So in this case, it's blue. So if you remember from the slide before, the blue was the actual instrument. So it tells you as well what instrument was actually, or sorry, what consensus mean was actually used for that comparison. We then have our 3 performance indicators. our standard deviation index, our target score, and our percentage deviation. Now, the other ones, the RM, are basically averages. So they're running means, and they're the average of the last 10. Once again, Sally will actually go through the actual statistics just in a moment. One thing really to mention with this is that the running means may average out performance issues. Because they can be positive and negative, then obviously if you're fluctuating around the mean, then you'll actually, an average will be closer to the actual mean itself. In that case, it can give a false indication of that your performance is actually better than it is. So what we would recommend is actually the use of the running mean target score. This was developed for us by Professor Tom Whitehead. Used to work with the WHO and then with the UK National Scheme for a long time before he sat on our advisory panel, and he developed this scheme for us. It's simply, it's always an absolute value, so it's always positive. So you're looking at a top score of 120 and a low score of 10. So you want to be as high a value as possible. Okay, the next box down is really just for information. It's giving indication of biological variation, although we have only recently this year removed that from the reports because that information was being updated. We have our acceptable limits of performance. That is based on our TDPAs. And also then we have the number of, well, basically if you fall outside of the top or bottom 5%, then it'll be indicated here that that's the case for your lab. Now, we used to write on here that you were excluded. People were getting confused in the past, thinking that was an indication of poor performance to say that you were excluded. To say you're excluded isn't necessarily the case that you have poor performance. It just means that your result is outside of our limits that we have set. But then that is indicated quite clearly on the report in this section. Just to go back very quickly just about the exclusions and the results, which are outliers. Sally, sorry, I'm just going to you talk about this in your next section, don't you, for the exclusions? Oh, okay. We took that slide out. Okay. I'll explain it quite quickly here. Then this was raised as part of the chat. Really, the exclusions. Why does a result get removed or not included in the stats? Well, we use a system at the moment called Chauvenet's criterion. Basically, what we do is we take all the results that get submitted and we generate a mean and a standard deviation from those results. Then what we do is depending on the number of returns, then we apply a factor. Any result, that factor then gets applied to that range. So basically what we have is a mean then and a range of results. Any results which are outside that range then get excluded for the generation of the target. So really what we're trying to do here is trying to remove any outside results, anything which is going to have a major impact on the overall spread of the data. So we do that system twice, and then what we have is a body of results where we then generate a mean and a 2SD range. Once again, any results which are outside 2SD range are then excluded for the generation of the target. And that target is what we display on the reports. So you have a target really plus a 2SD range. We can provide more information. We have worked examples for that. So if you want to see how that's done, then we can certainly send that to you. Just let us know if you want that information separately. The histogram provides really a very visual representation of how your results compares to your instrument grouping and the methods and the all methods. So once again, color coordinated, same colors as we had before. So we have your result represented by the triangle. We can see how that sits in the body of results for your instrument group, how your instrument group sits within the main set of results for your methods, and then all methods as well are represented by the other white bars. The two peaks at either side, or should I say, sorry, the two bars on either side represent any results which are outside of 3 standard deviations. Sally will go through this more later on with the troubleshooting, but it's a very useful way of very quickly determining how your result sits in with your peers. So quite simply, you can see, do you have a bias compared to your instrument group? Does your instrument group as a whole have a bias compared to your method, or vice versa? Does your method have a bias compared to the all methods, which in some cases is the case. So we'll talk about that more this morning as we go on. This is just an example of that, however, so where you can see that the instrument group itself has a bias. But you can see this one result here, which is completely sitting far off away from your instrument group, but yet it's actually sitting and it compares very well to the other main body of results. This would sort of indicate or give us a bit of a warning, basically to say, we would wonder, is this person here actually correctly registered in the correct instrument group? That's one possible reason. Another possible reason is that they have recently changed without informing us. So they may have changed their method, may have changed their instrument without actually passing that information on. So they would have then represented on the report, it would look like a bias, but it may be just that they're simply incorrectly registered. The multi-method start section is another way of then looking to see potentially if you are once again incorrectly registered. You may, for example, have new methods which are being released and or new standardizations that are coming online. So it's very useful then just to look at the method group breakdown just to see, do you compare with a different method? It's also useful, this section, really to look at once again, to say, are there, especially if you're looking to change instrumentation or change method, is there a method that performs more, but just basically has better overall performance than the one that you're currently using? One thing to look out for, of course, is where we have specific instrument groups which are split out, because in this case it's not always just the method. In this case here, we've had to split out the VTROS system, or specifically we may have a separate reagent manufacturer where we've split them off out of the main method groups. And because of that, then sometimes whenever you're looking at the CVs and you look at a specific CV, the CV itself may look good for that individual system, but that may be because it's actually relating to an instrument rather than a method. Okay, obviously a method group here will contain multiple instrument systems normally. The Levy-Jennings chart shows performance with time. And this would be very similar to what you would normally have or what you would experience in your normal internal QC, except you have to remember this is slightly different in that this is a combination of multiple concentrations. So what we have first of all is your current result being plotted on the right hand side as indicated here. And we go back in time over the case, normally of 20 plots, 20 samples. With regards to our bi-weekly schemes, that would be then normally 12 or 13 samples per cycle. In the case of our monthly programs, that would just go basically 12 results per the year or per cycle. So what we have here is current results. What we want is one, really to stay with the deviations, darker the worse the performance. Once again, very visual, just for a quick interpretation. You do have the concentrations of the consensus mean, basically, that has been used for each of the individual samples. You'll see this other letter here, which is either an I, an M, or an A, depending on what the actual consensus was that was being used, whether it was an instrument, a method, or an all methods target. A couple of other things just to note. Obviously, apart from the shading, is then you'll have a couple of other indicators here. You'll have a C if the result's been corrected. If you've had a non-submission, it'll be an N. We do allow corrections to be made for genuine reasons, for the likes of where the sample's been reconstituted incorrectly or there's been an error, and we basically approved the correction in that case. But those corrections really should be made within 4 weeks of the actual result date. So really by the time, if it's a monthly scheme, it'll be the next sample. If it's a bi-weekly, then it'll be 2 samples time. So there is a limited time frame to get those corrections in, but we do allow them. You are looking, as I say, for 2 standard deviations, really is what we're looking for acceptable performance. Target scoring chart provides a visual of the target scoring system. Once again, it's based on a simple absolute score, so you want to be up to a high score of 120 and a bottom score of 10. We're looking for target scores really of greater than 50, and Sally will go into that in more detail later on in the next section. Very simple again, just basically stay in the light shading, current result to the right hand side and moving back in time. The TDPA, which is highlighted here, relates to basically the CV that we have determined at what the limit is, and that is basically where you people would, or sorry, 90% of participants achieve a score better than 50. Sorry, just repeat that. So TDPA is based on the percentage that 90% of our customers can achieve that will give them a target score greater than 50. So basically if you have a plot which is greater than 50, that indicates you've got a CV which is less than this target. Okay, but Sally's going to go through that in more detail shortly. Percentage deviation by sample chart. Okay, just basically as it says, it's plotting percentage deviation rather than SDIs. Once again, current result, moving back in time. That performance limit is indicated, so this is our TDPAs, so this is the red bar, top and bottom, obviously for positive and negative values. That normally is defaulted to our TDPA, but we do have the ability to change that to make it country-specific requirements, which very few people actually use, but we do have the ability to change that. So we do have certain countries that would use different specific requirements, and this is where they'll be indicated on the reports. Thing to notice about this chart as well is that unlike the SDIs and unlike the Levy-Jennings, the scale will change from sample to sample and from parameter to parameter. So you have to be aware of the actual scaling on the actual chart itself. But once again, stay within the white area, out of the red. The separate plot here is apart from the black dots, which are the individual samples, you have the white circles, the open circles. These are running means. So these are running mean deviations, which are your average of your last 10. So for example, in this case here, for this plot here, this is an average of your last 10 results. Okay. So this does give you a very useful indication of performance over the concentration range that we have and over a period of time. But it is open to potentially a few problems in that if you do have one really bad result, then it will knock it out, as would be indicated, I think, here. So you've got one really poor result, which has knocked that running mean out completely until it's rectified, and you pass back your last 10 results. So useful for long-term interpretation of performance. And really what we would use this chart for is to doing more of a direct comparison between your internal QC and your external quality assessment. We'll talk about this later once again, but really at this stage, really all I wanted to explain is that whenever we're doing a comparison between our EQA and our internal QC, we normally wouldn't do it in terms of SDs. Well, first of all, because our SDs are different from the SDs, the different ranges that you're using in your internal QC. So in order to do a like-for-like comparison, then we look at both systems in terms of percentage deviation rather than SDs. And this will give us a better comparison between your internal QC and your external quality assessment. The last chart here, percentage deviation by concentration chart, once again gives us an interpretation of how your current result compares to previous results that you have analysed at a specific concentration range. So in this case here, your current result is presented by a black square, and what you'll see is the concentrations that you've previously measured. So in this case here, black square, current result, then other samples that you've measured along that concentration band, then you can see how you compare whether you've got a positive bias or a negative bias at a specific concentration. Similarly, has your result this time round, does it compare well with how you've performed previously as well? So you finish up with things like this, where you can see your current result matches very well at the top end concentration, but at the lower concentrations you've got a much wider spread of results, indicating that you do have a precision problem at the low end. Similarly here, current result matches very well with then your lower end, but as you can see, you'll have a positive bias in general at the higher concentrations. But what this chart doesn't show you then is the timeline. So what we don't know, for example, is for this result here, is this a result, is this an old result, which is just atypical at this concentration, or has your performance changed at all over time? So really what you need to do is to use all of the charts together. So you're looking at not only this chart with regards to concentration, but you also need to look at your timeline to see how your performance has potentially shifted over time. And Sally's going to go through that later on when we look at troubleshooting. So at that stage, I'm going to pass you over to Sally, and she's going to take you through some of the stats that we've already mentioned as part of the charts.
Okay, good morning or afternoon, depending on where you are. So as Stephen says, I'm just going to take you through some of the statistics that are used to calculate the different performance indicators that Stephen's just shown you on the reports. So we're an accredited EQA scheme, and we're accredited to ISO 17043, which is the standard for external quality assessment schemes. And as part of that, there's a whole section on statistical design, and we have to be able to prove that we match all the parts on this statistical design section of the standard. So the first one you can see here is fit for purpose performance evaluation intervals. So we're going to look at our 3 performance evaluation intervals and how each one of them is calculated. So we have our 3 performance indicators that Stephen has shown you on the report: the percentage deviation, the standard deviation index, and the target score. And each of these will show you the difference between your result and a target or an assigned value. So the percentage deviation will show your bias relative to the mean for comparison. Your target score shows the difference between your percentage deviation for this particular sample and compares that to a target deviation. And the SDI, the standard deviation index, is your bias relative to the SDPA, or the standard deviation for performance assessment. And we're going to look at how each of these different aspects is calculated. So the standard deviation index is your result minus the mean for comparison divided by the SDPA, the standard deviation for performance assessments. So the SDPA will look at how that's calculated for each particular sample. The percentage deviation is just a normal routine percentage deviation calculation. So it's your result minus the mean for comparison divided by the mean for comparison times 100. And then we take that percentage deviation and we compare it to the TDPA, or target deviation for performance assessment, that we have set for each different analyte. As Stephen said, that's the value that's set where 90% of the labs would be deemed to have acceptable performance. So we take the lab's percentage deviation, compare it to the TDPA, multiply by 3.16, take the log 10 and multiply by 100. And at that point, your brain has probably all switched off because you're going logarithmic calculations. We don't like those. So the take-home message is this bit at the bottom. So we're going to look at the lab's percentage deviation for this particular sample. If it's equal to the TDPA value, the target score the lab's going to get is 50, which, as Stephen said, is the value where you are deemed to have acceptable performance. If your percentage deviation for this particular sample is greater than the target deviation for performance assessment, your target score is going to be less than 50, and you're going to be deemed to have unacceptable performance for this particular sample. But if your percentage deviation is less than the TDPA, so you've performed better than the target we've set where 90% of labs can perform well, your target score is going to be greater than 50 and you're going to have acceptable performance. So that's the take-home message there at the bottom. It's all about the target score being equal to or greater than 50 to have acceptable performance. So this is just to sum up our 3 performance indicators. So for acceptable performance, your SDI should be less than 2, your target score should be greater than 50, and the percentage deviation should be less than the acceptable limits, which in most cases, as Stephen said, will be the RIQAS TDPA, or target deviation for performance assessment. So the next part of the standard that we have to meet is we have to show that any known aspects of variability in the samples are not going to affect laboratories' performance evaluation. So we calculate our TDPAs, and these are set for each individual parameter. So when we're looking to calculate the TDPAs, we look at the CVs from the previous samples and set a target CV, but we also have to look at the potential variability in the samples. So we look at the testing of the homogeneity, reconstituted or real-time stability, and shipping and transport stability of the samples. So in order to assign the TDPAs, we look at these 4 different areas, and we look to see which of these is going to have the highest value. So as Stephen said, our calculated target deviation is assigned where 10% of the labs would have poor performance, a target score less than 50. We look at our test homogeneity, our test stability data, and our transport differences, and we multiply each of these by 3.33, and then we look to see which of these is the highest, and that is set as the TDPA for that particular analyte. And just in case you're wondering why we didn't just pick 3.33 out of the air, in the UPAC clause of the statistical standard, it talks about the sample variability should be less than 30% of the evaluation interval. So that's where our 3.33 comes into it. So by multiplying by 3.33, we're finding out which of these is the highest, and then that's what we set as the TDPA. So only 2% of the parameters would need to be adjusted due to any sample variability, which just demonstrates that we have excellent materials, and the TDPAs are generally based on that calculated target deviation where 10% of labs would have poor performance. So again, that's just to highlight where the TDPA comes into the calculation of your scoring. So it's used in the calculation of the target score for each sample. So the evaluation intervals are the thing that we are comparing the lab's performance against. So the TDPA is the same for all samples and all concentrations and only changes annually, but it will be different for every parameter on the report. The SDPAs, or the standard deviation for performance assessment, are different for different samples, and that's because it will change depending on the concentration of the sample, because the mean for comparison is used to calculate the SDPA, which we'll see next. So the standard deviation for performance assessment is used to calculate your standard deviation index, your SDI, and it's calculated from the TDPA value times the mean for comparison divided by the t-value times 100. So the t-value in this calculation is the factor which represents the percentage of poor performers reflected in the TDPA. So if you know statistics, at the 90%, which is where 10% of labs achieve poor performance, your t-value would be 1.645. So for the majority of the parameters, the t-value in this calculation will be 1.645. For the few parameters where we have to adjust due to the sample variability, the percentage here changes, so the t-value changes, and then that's where it's used to calculate your SDPA. We don't want to go into overload on statistics, so if you do need any more information or want any more information on it, if you want to either leave a note in the chat or else contact your local Randox representative, they can let us know and we can send you through additional statistical information. So the next part of the standard is we have to show that we have fit for purpose assigned values, which shows that we have to have appropriate handling of the gross outliers and appropriate handling of the statistical outliers, which is what Stephen was explaining earlier in the outlier process. So we take out our gross outliers. So these are likely to be any results that have been returned in the wrong unit. So sometimes labs, when they're registering, manage to pick the wrong unit. They mix up millis and micros, so they end up out by a factor of 1,000. So we can see clearly that those are gross outliers, and we don't want those to be included in the statistics that's used to calculate the mean for comparison. So those are taken out and aren't included in the statistical analysis that are done. So they're marked as deactivated and will appear on the report in that excluded section that Stephen was highlighting. So once we've taken out the gross outliers, as Stephen said, then all the results that are left go through the statistical outlier process, and then we're left. So we go through our Chauvinet's criterion, our 95th percentile, and the results that are left are then used to calculate that mean for comparison that is used. So as Stephen pointed out, we have the excluded results shown on the report. So in this instance, there were 86 results used to calculate the mean for comparison here for creatinine and 10 results have been excluded either as gross outliers or during the statistical processing. These outliers generally, as you can see here, represent about 5 to 10% of the results that have been returned. So the last part of the standard for the statistical design, we have that we're using robust statistics to calculate the consensus means for comparison. And for each of these, we have to assign the uncertainty of the mean for comparison, or the assigned value. So this is just a clause. Because we're using a consensus value, the proficiency testing provider shall document the reason for that selection and shall estimate the uncertainty of the assigned value as described in the plan for the proficiency testing scheme. So in order to calculate the uncertainty for each of the means for comparison that appear on the report, this is our calculation. So it's 1.25 times the standard deviation divided by the square root of the number of results used to calculate the mean for comparison. And this must be less than 0.3 times the SDPA. So the SD in this instance is just the calculated SD from the consensus of the results. So when we're calculating the mean for comparison, we calculate the standard deviation and the CV of that particular peer group. And in this instance, to calculate the uncertainty, we use the standard deviation of the consensus results. So once we have calculated our uncertainty, we compare it to 0.3 times the SDPA. If it's greater than 0.3 times the SDPA, it's considered to be significant and needs to be combined with the SDPA. And this is how we do it. So this is how you pull any data sets whenever you're pulling your data. So you take your uncertainty and square it. You take your SDPA and square it. You add them together and you take the square root, and that will give you your adjusted uncertainty. If your uncertainty is less than 0.3 times the SDPA, it's considered insignificant. So the SDPA adjusted is just the SDPA value that has been calculated. So we show this on the reports if the uncertainty is large enough that it is deemed to be significant. We show it under the SDPA column. You can see here the little A's beside the method SDPA and the instrument SDPA. So that shows that here you can see the uncertainty is a large value. So it has been incorporated with the SDPA and is shown here by the little A. So where does the SDPA then come into it to identifying the lab's performance? So it's used in the SDI calculation. And here you can see the SDI is the participant's result minus the mean for comparison divided by the SDPA adjusted. And this is the SDI then that is shown on the report on the Levy-Jennings chart, as Stephen has already shown. So here you can just, again, this is in the results section that you saw at the start. Here you can see our 3 performance indicators are all indicated. Our SDI target score, percentage deviation, and Stephen said the running means are here as well. So, but here the SDI is calculated using the SDPA adjusted, and the target score is calculated using the TDPA value.
Yeah, just to really, we've just got a couple of additional pages just to go through before we get to the end of this section. So we've gone through each individual analyte page. So at the back of the report, you'll come to the summary page, which is, as the title suggests, is a summary of the overall performance that you've seen for this individual sample. So, but it's useful in itself where you may not pick up a problem looking at the individual parameter page, actually looking at the summary page where all the information is gathered together. You can quite quickly discover some problems that you may have had with the measurement of this individual sample. I'll just mention two, although Sally will go through them later on in more detail. Just really reconstitution problems and basically where you've measured the wrong sample can be very easily picked up on your summary page, where it's more difficult to detect on your individual parameter page. You'll notice then as well some results here which are highlighted in bold, underlined, and you'll notice the red triangles. So just to explain those, so really what we have here are where each or three of your performance indicators have fallen outside of the limits. They will be in bold and underlined just to draw your attention to them. And if all three fail, then basically this is where you'll have your red triangle. So quite simply, turn to your summary page, look to see if you have any red triangles, and that's the first port of call, first parameters that you need to look at if there are any problems. You will, of course, this doesn't mean that you don't look at the other parameters, because you don't know really by looking at this whether you have the development of any trends or any sudden shifts in performance. This, however, does give you a very quick representation, visualization of which ones you need to look at first of all, because there's a specific problem with these parameters. So that's the end really of the routine report, but it's also presented, that same information can be presented in a couple of additional reports then, if you're part of a group or you have multiple instruments within your lab, which is very often the case. So we present this in two different ways. First of all, there's a PDF format, and also then there's a CSV format. So look initially at the summary in PDF format, and here you can see if you are part of a large group or if you have multiple instruments within the one lab, then what you can have is a report like this. And really what we have is, just zoom in here. So you've got your current result, current sample indicated on the right hand side, and your 9 previous samples going back in time. If there are any which fall outside of your limits, these will be highlighted in red, so you'll see them as well. But as you can see, going from the chart, really what you're looking for here is basically, are there any individual instruments, any individual customers, if you're part of a group, that are basically outside of the norm from the others, or if you have any individual samples which are performing poorly. So, but as you can see, it is fairly cluttered there. We limit it to 15 to one individual chart just because of that. So if you have more than 15 participants within your group, then it'll be broken down over multiple charts. So that's not ideal for that sort of scenario. So what we then do is provide it in CSV format. So if you're part of a large group, part of a large chain of laboratories, or if you're part of a large trust and you want, you have the role of being a coordinator within that trust, then this is a very good idea of getting all the data back in a CSV format. Well, basically a CSV, so you open it up, it'll open up an Excel or some other spreadsheet. But really, it looks like a lot of information, and you maybe say to myself, well, how does that help me? But because it's in Excel, there are so many different ways that you can look at it very quickly to pull out the information that you need. So first of all, do you want to filter by instruments? So if you're looking for a specific instrument, simply add filters and you can filter by instrument. Specific customer, look at just their performance for that individual participant, simply filter by the registration number. Okay, if you want to see how your overall performance works within your group, then sort by parameter and result. And this will give you then how each of your individual instruments, especially if you're in this, I use the example here of the blood gas because obviously this is one situation where you will have a lot of different instruments covered within your lab or within your hospital situation. If you add in conditional formatting, so it's very easy to do that, and you can then basically very quickly then look at which individual instruments, which individual registrations then are performing poorly or performing worse or better than others. You can use it, of course, just to look at the same sort of situation where you would have the red flag, the red triangle that we looked at on your standard report. These are indicated on this with the asterisk, and this is the same, represents this red triangle. So you can look at once again, simply filter on performance, and you can very quickly from a very large list hone in very quickly on just those individual parameters or instruments which are for performance. So I would certainly recommend, if you're part of a large group of laboratories and you are the coordinator, to get this information as part of the CSV format. Okay, so once we get to the end of our cycle, then we have an end of cycle report, which will summarize all the samples that we've had over the past cycle. So basically the charts are the same. So you have the same Levy-Jennings, percentage deviation, target score, and percentage deviation by concentration. But if you notice here, limited to just the number of samples from within the cycle. So it's really just looking at that cycle information. Together with it, just a summary of the stats from that cycle as well. So one of the other things you'll notice then is we give a comparison to the previous cycle compared to the current cycle. And this gives you just a bit of an indication of just how your performance has changed, potentially better or worse from the previous cycle. We look at it in terms of absolute SDIs and absolute percentage deviation, absolute scores, so that we take out the averaging. So remember we talked about previously where if it's positive or negative, then it may basically average out and your performance may look better than it actually is. So we look at absolute scores in this case, so that you're just looking at the magnitude of the deviation rather than being influenced by the potentially positive negative results. One thing why we look at absolute scores and specifically SDIs is we don't have target scores set for every single parameter. And because of that, we will have an SDI for each individual, for every single parameter, quantitative parameter that is. So that's why we use SDIs in this case and not the target scores. So really what else to look at? So that's that goes through for every single parameter page on your end of cycle, gives you that summary. But once again, there's an overall summary then towards the back of the end of cycle report, which is slightly different. And this gives a graphical representation of your absolute SDIs over the cycle. And in this case, what we do is we compare your lab's SDI, should I say your cycle average absolute SDI in this case, but that average SDI, we compare your result to the average for the country. So whether it's UK or, and for those members joining us from Lithuania or Slovenia, so this will look at then country-specific performance. Also is that the W stands for world. So you have here, so L laboratory, C country, and W for world. So in this case here, this is your result for the current cycle. This is your lab. So for albumin, this is 0.64 SDI. So you can see that you're slightly worse than last cycles. If you're worse than last cycle, it'll be plotted on the bar here with a red dot. If your performance is better than last cycle, it'll present it with a green dot. Okay, basically the open circle here is the performance from last cycle. So last cycle, these are the last cycle's performance. So you can see whether you're worse or better. And it's very, very quick representation, very easy just to see, has your performance shifted better or worse? Now, we use the word worse. Some people don't like us using the word worse, but we couldn't think of a better word. It doesn't mean it's bad. It doesn't mean that you've got poor performance. And as you can see in all these cases, the performance is still good. It just means that it's not as good as last cycle. Okay.